All right, if you're building enterprise AI apps right now, you definitely know this exact sinking feeling. You open your infrastructure bill at the end of the month, and your costs have just quietly skyrocketed. It's a massive problem across the entire industry right now, and it's driven by what's known as the single model default trap. But don't worry, because in this explainer, we're going to unpack exactly how you can escape that trap. We're looking at some brilliant architectural blueprints from Paul Ranjan's work on token economics, focusing on how designing multi-model portfolios, or what's called the triage engine, can literally save you 40 to 70% on infrastructure right out of the gate, all without sacrificing a single drop of quality.
Okay, let's dive into this. To really grasp the root of the problem, you just have to look at this perfectly absurd reality. You don't send a surgeon to take out the trash, right? It sounds ridiculous, but in the AI world, developers are doing exactly that every single day. We are taking the most advanced, expensive, computationally massive frontier models on the market, and we're using them to do things like basic text routing, simple summarizations, and just everyday data extraction. It's an unbelievable drain on resources and your budget.
To see why this is such a budget killer, we have to contrast that standard setup with a much smarter alternative. In the default frontier paradigm, every single user request slams into your biggest, smartest, most expensive model. And because AI generation is inherently sequential and bound by memory, this approach is agonizingly slow. It's just massive overkill for basic tasks. But then you have the triage router approach, which completely flips the script. Instead of relying on this giant monolith, you use a dynamic task routing system that delegates tasks based on how complex they actually are. It gives you blazing speed, makes the whole architecture highly cost-effective, and quietly stops those silent budget leaks. There's a great analogy from the text that makes this instantly click. The emergency room triage. Think about how a real hospital operates. When someone walks into an ER, they don't immediately get rushed to the hospital's top chief surgeon, right? That would literally bankrupt the hospital and create insane bottlenecks. Instead, they see a triage nurse. That nurse is fast, highly efficient, and makes a split-second routing decision. A scraped knee? That goes to the bandage station. A routine fracture? Resident. Only the absolutely critical, complex cases ever make it to that specialist surgeon. Our AI systems desperately need that exact same kind of lightweight router to direct traffic. And this brilliantly illustrates what that optimized traffic distribution actually looks like in practice. It's an eye-opening split. A whopping 70% of everyday AI requests can be completely seamlessly handled by a fast, small model. Then you've got about 25% that need a mid-tier model. But the huge aha moment here is that only a tiny 5% fraction of your tasks actually require the deep, high-stakes reasoning of your chief surgeon frontier model. So if you're sending 100% of your traffic to that 5% model, you are basically just setting cash on fire. So how do we actually build this thing? This architecture is known as the 3-tier portfolio blueprint. At the very top, you've got your frontier model, and that is strictly reserved for complex reasoning and high-stakes output. In the middle, your mid-tier workhorse takes on everyday standard generation. And down at the base, your small, super fast model acts as your triage nurse. It handles the classification, the routing, the summarization. Now, the main reason this blueprint is an absolute game changer is the price gap. The cost difference between these tiers is usually between 10 to 60 times. 60 times. So shifting a task from the top down to the bottom doesn't just save pennies, it completely revolutionizes your unit economics. Now, I know what you're thinking. Knowing this is one thing, but actually implementing it is another. And there's a trap here that engineering teams fall into all the time. You might even recognize this from your own sprints. It's called the temporary frontier. Here's how it plays out. A team is prototyping some cool new feature, and to make sure it works perfectly, they build it on the absolute largest, most powerful model they have. They tell themselves, hey, we'll just ship this temporarily to get to market, and we'll optimize it to a smaller model later. But let's be real, production schedules get crazy, new features pile up, and later never actually happens. So that temporary shortcut just becomes permanent architecture, and costs absolutely spiral as soon as user traffic scales up. So the crucial point is how we implement the right routing to avoid all that. There are a few different strategies you can pull from. First, you got static routing, which is pretty straightforward. You just route things based on the endpoint or the task type. Then you step up to dynamic routing, where a lightweight classifier actively scores how complex an incoming prompt is and dispatches it on the fly. Honestly, that alone can capture those 40 to 70% savings.
You can also use fine-tuning and distillation, where small, specialized models actually beat the big general ones on both cost and quality. But for my money, the most fascinating strategy of all is the cascade.
The cascade escalation is just this incredible procedural loop. It essentially gives you the dirt cheap costs of a small model, but with the massive safety net of a frontier model. It's a simple three-step process. Step 1, you attempt the task on your absolute fastest, cheapest model. Step 2, you don't just blindly accept the answer. You run it through an evaluation gate to validate the quality. And then step 3, if and only if the cheap model fails that check, you escalate that exact same task up to the expensive frontier model. It's brilliant because it keeps production super safe without sacrificing quality, all while defaulting to the cheapest path possible. Now, what's really interesting about this specific workflow is visualizing that escalation path. The request comes in, hits the cheap model, and then there's that critical moment, the failure path, that triggers the escalation. But the absolute magic here, the whole secret sauce, is that quality gate in the middle. How do you even know if the cheap model messed up? Well, you can use confidence scores, strict schema validations, or even an LLM as a judge setup to verify the work. That gate is literally what converts those massive price gaps into real money back in your pocket.
But, and this is a really big but, there is a major nuance here you have to watch out for. It's called the double payment trap. Cascades sound mathematically beautiful, but they only actually win if your first pass success rate is high enough. Just think about it for a second. If your cheap model is failing 90% of the time, and you're forced to escalate 90% of your traffic to the expensive model anyway, you're definitely not saving money. In fact, you're losing it. Because now you're paying for the failed attempt on the cheap model and the successful one on the frontier model. So your cascade absolutely must be tuned so the cheap model is actually getting it right on a large chunk of those requests.
Let's move to and see how this builds into an entirely new way to measure AI performance. It brings up this really fantastic concept called goodput. Goodput is defined simply as the tokens produced at the quality level the application actually requires. This is so vital because it finally ties your architectural decisions directly back to actual business value. We really have to stop just cheering for raw, blind output and start measuring the stuff that actually solves our users' problems. Because when you compare the two, the difference is night and day. Raw throughput is just counting every single token your system spits out, completely ignoring whether those tokens are accurate or hallucinated or just totally useless. But goodput forces you to judge your costs while holding quality strictly constant. The golden rule here is that any optimization you make, whether you're tweaking routing or caching or prompting, has to be judged by keeping your quality locked in with one of those evaluation gates and only cutting the costs from there. Because let's be honest, cutting costs by just degrading your quality isn't optimization at all. It's just breaking your product. And the math behind goodput is honestly kind of wild and very empowering. Say you have a cheap model that's failing 30% of the time. Your first instinct is probably to just rip it out entirely, right? But the math actually says, wait, if those 30% failures are safely caught by an evaluation gate, and then you just retry them, or escalate them, or send them to a human, that setup is often way more economical than just paying a premium for 100% success on a massive frontier model. When the price gap between models is 10 to 60 times, you can literally afford a ton of retries on a cheap model and still come out massively ahead. A dynamic multi-tier cascade really does cut costs, not corners. Which brings us right back to where we started. I want to leave you with a final thought that really challenges how most technical teams are operating right now. Based on that quote from earlier, you really have to ask your own organization, who is taking out your AI trash? Are you seriously paying premium rates for a digital chief surgeon just to sort through basic everyday data extraction? It is definitely time to audit your architecture, stop relying on those lazy single model defaults, and start designing your own triage engine. Seriously, those 40 to 70% savings are just sitting there. You just have to claim them.